So let's come to our today's topic, that is alternating current, NCERT section 7.4, example 7.2. So let's begin. So this is the disclaimer. Learning objective: after this lecture you will be able to understand the instantaneous current, inductive reactance, instantaneous power, average power, phasor diagram and phase relationship between the current and voltage of purely inductive circuits. Okay, so this index of topics that we are going to discuss today is NCERT section 7.4, that is AC voltage applied to an inductor. Now we will discuss purely inductive circuit. Secondly, example 7.2. So let's begin. So purely inductive circuit. So what is purely inductive circuit? Consider what was purely a resistive circuit, the circuit containing resistor and voltage source. Similarly, consider a circuit containing a pure inductor L connected to an AC source generating AC voltage that is equal to V equal to Vm sin omega t. So this this inductor is connected to a AC source, and this AC source is generating the AC voltage which is equal to Vm sin omega t. Okay, like this. This inductor is a form of, it is similar to solenoid. Okay, a coil that is closely wound and having a number of turns. So this is inductor having self inductance L. Okay, and this is AC source connected to this inductor. Figure 7.5, an AC source connected to an inductor. Inductors have appreciable resistance in their windings. So they are made of a conducting coil. Okay, so this conducting coil may have some appreciable or significant resistance also, but we shall assume that this inductor has negligible resistance. We will assume that resistance between the windings is zero. Resistance to the flow of current in the windings is zero. We will not assume resistance here to avoid the complexity in the final expression. We will only derive for inductive reactance. So what is the reactance, or we can say opposition, offered by this inductor to the flow of AC current? Okay, not by resistance but by inductive reactance. Okay, what is inductive reactance? We are going to discuss it later in these slides, in the further slides. Okay, so we are neglecting the resistance in the windings. Does the circuit is purely inductive? Okay, there is no resistance in the winding, so purely inductive circuit. We will not take into account the effect of the resistance in the windings. So the circuit is a purely inductive AC circuit containing inductor and voltage source only. According to Faraday's law of electromagnetic induction, magnitude of induced EMF in a circuit is equal to the rate of change of magnetic flux through the circuit. Okay, so we have discussed for self-induction. Okay, so we have discussed the self-induction topic, and according to Faraday's law of electromagnetic induction, we know that induced EMF in a circuit is equal to a rate of change of magnetic flux through the circuit. Okay, so mathematically induced EMF in the inductor is given by, so we have seen this expression in the self-inductance topic. Okay, so if this inductor is having some self-inductance L, so EMF induced in this inductor is given by equation 6.14 of chapter electromagnetic induction, that is equal to minus L di by dt, and negative sign is representing the polarity of the EMF. That means EMF will be induced in such a way, according to Lenz's law, that it will oppose the cause. If current is increasing in one direction, it will oppose the increase in current by inducing EMF in the opposite polarity, or inducing current in the opposite direction. So this induced EMF is equal to minus L di by dt. So at any instant, let's suppose at any instant current in the circuit is increasing in the clockwise direction. So current is increasing in the clockwise direction, and we are also moving clockwise across the room. So this is diagram. So you can assume that current is increasing in the clockwise direction, and we are also moving in the clockwise direction. Okay, so current is increasing in the clockwise direction, mean it is flowing in the clockwise direction, means at some instant there is positive on the above of this AC source, there is positive, in the below part there is a negative terminal at any instant. Okay, so current is increasing. So why we have written increasing? because if current will increase, EMF will be induced to oppose the increase of current in the opposite direction. Okay. So according to Kirchhoff loop rule, the voltage gain or drops across a loop, closed loop, will be equal to 0. So sum of all the potential gains and drops across the closed loop will be equal to 0. Means if we are moving clockwise, so moving across this voltage source, so this voltage will be taken as positive. Now we have reached this inductor. So EMF induced is equal to minus L di by dt. Okay, so EMF is induced in the opposite direction. It is opposing the increase in current. So it is epsilon equal to minus L di by dt. So it will be added up like this. So voltage, we are moving clockwise and considering this voltage V, and we have reached this L. So voltage and EMF induced across this inductor is equal to minus L di by dt, and sum of both these voltages will be equal to 0. Okay, mark this equation as 7.10. So we have found the expression, this V minus L di by dt equal to 0. So expression for current in purely inductive circuit, we will derive the expression for purely inductive circuit by using this expression, V minus L di by dt equal to 0. So putting the value of V equal to Vm sin omega t, equation 7.10 becomes Vm sin omega t equal to L di by dt. Okay. Now di by dt, after rearranging this equation, di by dt will be equal to Vm upon L sin omega t. So mark this equation as 7.11. Okay. Now to find the phase relationship between current and voltage, we need to find the current across the inductor as voltage is already given. So voltage is given, V equal to Vm sin omega t. In purely capacitive circuit, we are also going to use the voltage V equal to Vm sin omega t. So this is fixed. Only we will derive the expression for current. Okay. So for current in the purely inductive circuit, we applied the Kirchhoff law in the loop. Okay. Now we have come up to this expression. After putting the value of V, we have reached this equation, di upon dt equal to Vm upon L sin omega t. Now we will find the current from this expression. How can we find? By integrating. This is di, we have to find the I. So after integrating, so to find the phase relationship between current and voltage, we need to find the current across the inductor as voltage is already given. Okay, so di by dt equal to Vm upon L sin omega t. This is equation 7.11. To find the current I, we integrate above equation with respect to time on both sides. So di, this dt will go there. So di equal to Vm upon L sin omega t dt integration. So Vm is constant, L is constant. So it will come out of the integration. So in the integration, it will be sin omega t dt, and here di. So there are no limits. So this is indefinite integral. So di will become I equal to Vm upon L sin omega t. Derivation of integration of sin omega t is equal to minus cos omega t upon omega. Sin omega t is equal to integration of sin omega t dt is equal to minus cos omega t, and upon derivative of this omega t function, which will be equal to omega. Okay, so omega will go, come out. So Vm upon omega L after integration minus cos omega t. Now these are indefinite integrals, so plus c. Okay, constant of integration. So where c is constant of integration. Since the current oscillates symmetrically about 0, average of current over full cycle should be 0. So average current over full cycle is 0. We have discussed. Over pure resistive, for purely resistive circuit, it was 0. For purely inductive circuit, it is also 0. Okay, because current is oscillating symmetrically. Current is equal to cos omega t. It is the function of cos omega t, any sinusoidal function. Okay, so it is oscillating about 0 in the symmetric way. One positive cycle, one negative cycle. Okay, and positive and negative cycle are symmetric. Okay, due to which average current will be So positive current and negative current will be equal. So average current over full cycle will be 0. Okay. So taking average on both sides of equation, this equation I equal to Vm upon omega L minus cos omega t plus C. So taking average on both sides of this equation, so I average. So I average, we know that it is equal to 0 due to the symmetry which is of the current across the 0. So I equal to 0 average I, which is equal to minus Vm omega L. These are constant value, they will come out of the average. Their average will be they also, means average of Vm is Vm, average of omega is omega, and average of L is L, because they are constant. So average of cos omega t plus C. So what is average of cos omega t? We have discussed some average values, some standard average values of sin omega t, cos omega t, sin square omega t, and cos square omega t. Okay, so average of cos omega t is, so average of cosine function over one full complete cycle is 0. So average current is 0. This cos omega t also 0, means this term will also become 0. So 0 equal to 0 plus C. So C is equal to 0. So C came out to be 0, constant of integration. So this expression of this I will become I equal to minus Vm upon omega L cos omega t. Okay, so we have found the constant of integration. So it came out to be 0. So this expression for this current will become like this: I equal to minus Vm upon omega L cos omega t. Okay, now we have to eliminate this negative sign. So I equal to Vm upon omega L cos omega t. Now using minus cos omega t. So what is cos omega t? By using the trigonometric identity, sin 90 minus theta is equal to cos theta. Cos 90 minus theta equal to sin theta. ठीक है, this property. Okay, conversion property. So cos theta will be equal to sin 90 minus theta. 90 is represented in the pi radians, pi by 2. So sin pi by 2 means 90 degree. Sin pi by 2 minus omega t. So consider this omega t as angle theta. So sin 90 minus theta will be equal to cos theta. So sin pi by 2 minus omega t will be cos omega t. Okay, so minus cos omega t will be equal to minus sin pi by 2 minus omega t, and we will this negative sign will go there inside the angle. We know that sin minus theta is equal to minus sin theta, but cos minus theta is equal to cos theta. Cos will not omit the negative sign out of the angle. Okay, if there is a minus theta, there is cos minus theta, and minus sign is with theta. So cos will not, so negative sign will not come out, because cos will digest it, you can see. Okay, but sine will, in the expression of sine minus theta is equal to minus sine theta. So sine will, in the case of sine, negative sign will come out of the argument of sine. Okay, so sine minus theta is minus sine theta. So it is going in reverse. If minus sine pi by 2 minus omega t is there, so negative sign can go inside also. So negative sign will go inside. So sine omega t minus pi by 2. Got it? So this is minus cos omega t will become sine omega t minus pi by 2. So for expression of current will be finally equal to Vm upon omega L sine omega t minus pi by 2. Now you can see phase is not same. In case of voltage, what was the instantaneous voltage? V equal to Vm sine omega t. The phase of the voltage was omega t. Phase of this current is omega t minus pi by 2. There is some initial phase. Okay, now we will see the phase relationship, where Vm upon omega L, this term, represents the amplitude of the current. So this I equal to Vm upon omega L. So this Vm upon omega L we can write Im. This is the amplitude of the current, that is Im. So expression for current in this case is equal to I equal to Im sine omega t minus pi by 2. This is the final expression, and mark it as 7.12 equation. So compare this Im equal to Vm upon omega L. Okay. Now amplitude of current is Im equal to Vm upon omega L. Now comparing it with Im equal to Vm upon R. Now you can see in the purely resistive circuit Im was equal to Vm upon R, and in inductive circuit Im is equal to Vm upon omega L. Okay, this is current, this is voltage in both cases. Means this omega L is having same units as resistance, or we can say this omega L is analogous to resistance in the resistive circuit. Okay, so comparing with Im equal to Vm upon R as in pure resistive circuit, here also omega L is analogous to the resistance in this case and is called the inductive reactance. So this term omega L is called the inductive reactance. So this R is the resistance in the resistive circuit. Okay, so same role is being played by the omega L in the case of inductor. So this is the inductive reactance, that is the opposition offered by the inductor to the flow of current. This resistance is the opposition offered by the resistance, or we can say resistor, to the flow of current. Okay, so omega L is analogous to the resistance and is called inductive reactance, denoted by XL. So this XL symbol is for inductive reactance. Inductive reactance limits the current in a purely inductive circuit in the same way as resistance limits the current in the purely resistive circuit. Okay, it helps in limiting the current, means it will determine the value of current with respect to voltage. Okay, so it limits the current in the purely inductive circuit in the same way that resistance limits the current in the purely resistive circuit. So what is the definition? So inductive reactance is the opposition offered by the inductor to the flow of alternating current. Okay, what is resistance? It is the opposition offered by the resistor to the flow of current. Okay, so XL is equal to omega L. Mark it as equation 7.13. So SI unit of XL is also ohm. Okay, because Im equal to Vm upon R and Im equal to Vm upon omega L. So this omega L is having unit same as resistance. So resistance, this omega L is equal to XL. So XL is having same SI unit is ohm. Inductive reactance is directly proportional to the inductance. So inductive reactance is directly proportional to inductance L and also directly proportional to the frequency of the current. This omega is the angular frequency and it is represented as 2 pi nu. So this XL can be written as 2 pi nu L. So 2 pi is constant. So this XL is also proportional to the frequency nu. Got it? So root mean square and peak current in the purely inductive circuit. So expression Im equal to Vm upon omega L can be written as Im equal to Vm upon XL. Okay, so this is the expression for the peak value of current. Mark it as 7.14 equation. So for DC current is having no angular velocity, no angular frequency, or no frequency, simple frequency. Okay, because it is not changing its polarity, it is not changing its direction periodically, so that's why it is not having any frequency. Okay, so means omega is 0 for the DC current. Its value is steady or variable, but its value is not changing periodically. So if it is not a periodic function, okay, it cannot be represented in the form of sinusoidal function or periodic function, then frequency is 0. So frequency of DC current is 0. That means XL will be equal to 0. XL is equal to omega L na? So if omega is equal to 0, so XL is equal to 0. So pure inductor offers no opposition to the DC. Okay, so if inductor is connected in the DC circuit, if DC source is used, there will be no opposition offered by the inductor. Got it? So inductor will offer no opposition to the DC current. Using relation Im equal to root 2 IRMS and Vm equal to root 2 VRMS. So put here Im equal to root 2 IRMS and put Vm equal to root 2 VRMS. So root 2 and root 2 will get cancelled out. So new expression in the terms of IRMS. Then from equation 7.14, it will also be true that IRMS equal to VRMS upon XL. So in the terms of IRMS. Let's see phase relationship now. Now relation for voltage and current across pure inductive circuit is respectively V equal to Vm sin omega t and I equal to Im sin omega t minus pi by 2. This current, we have derived the expression for the current, and we have assumed same for all the cases, for purely resistive, purely inductive, purely capacitive. So voltage will be equal to, we are using the same source, V equal to Vm sin omega t. Only we will derive the expression for the current, which is I equal to Im sin omega t minus pi by 2 in the case of purely inductive circuit. So if we take the phase difference, now take the phase difference. So phase difference will be equal to phase of current minus phase of voltage, which is equal to omega t minus pi by 2 minus omega t. So it will come out to be minus pi by 2. So we are taking phase of I with respect to voltage. So phase I minus voltage for phase of I with respect to voltage. So it came out to be minus pi by 2. It means current lags behind. So we are finding the phase of current with respect to voltage. It came out to be minus pi by 2. It is in the negative sign. So negative sign represent it is lagging behind the voltage. So current lags behind the voltage by a phase angle of pi by 2, or we can say 1/4 cycle. Okay. So phase of current with respect to voltage is came out to be minus pi by 2, means it is lagging behind, current is lagging behind the voltage by a phase angle of pi by 2. So phasor diagram representation. So this is a phasor diagram representation of the current and voltage. So if voltage at any instant, voltage vector, or we can say this phasor of voltage is represented as this by this blue phasor, and having at any time t1, it is having phase omega t1. So current will be lagging behind the voltage. Current will be having minus pi by 2 angle, means angle, we are measuring angle in the anti-clockwise direction. If we measure the angle in clockwise direction, it will be negative. So in the clockwise direction, current will be in the clockwise direction by pi by 2. Okay, current is lagging behind the voltage by pi by 2. That is the meaning of this phase difference. So current is lagging behind the voltage by pi by 2, 1/4 cycle. Okay, and in this graphical representation, you can see this voltage is starting from 0. Okay, now current is lagging behind the voltage. So it will start from not from the 0 value, it will start from the minimum value. It is lagging behind the voltage. Okay, so it will start from the minimum value and it will reach 0 after pi by 2. For half cycle, it is pi. For 1/4 cycle, it is pi by 2. So it will reach 0. This voltage is at 0. At time equal to 0. So, or we can say omega t equal to 0. At omega t equal to 0, voltage is at 0. At omega t is equal to pi by 2, current will reach the 0 value. Means current is lagging behind by pi by 2/4. Okay. This is the meaning of this phasor diagram and graphical representation, and this is the phase relationship for purely inductive circuit. So figure 7.6a shows the voltage phasor V and current phasor I at some time t1. So at any time t1, figure 7.6 shows the voltage phasor V and current phasor I. So figure shows that at some instant, voltage phasor V is rotating ahead of current phasor I by angle of pi by 2. Or we can say current is lagging behind pi angle pi by 2 with respect to this voltage phasor. Okay, when rotated with frequency omega anti-clockwise, these phasors generate the voltage and current given by the equation 7.1 and 7.12 respectively as shown in the figure 7.6b. So this is the graphical representation. So by viewing the graphical representation, it is hard to determine what is the phase difference between V and I. But by viewing or analyzing this phasor diagram, it is easy to visualize that what is the phase difference between voltage and current. That's why phasor diagrams are more in practical use in this chapter. Okay. So by meaning of this means this current You can see the dashed line in the graphical representation. Current is reaching its zero value after pi by 2 interval, or we can say after omega t equal to pi by 2, and voltage is pi at 0 on the 0. Okay, means current is lagging behind. Current is reaching the same value 0 after pi by 2 interval. It means it is lagging behind by pi by 2 phase. Got it? I hope you understood this thing. Now again this phasor diagram. So projection along y-axis. So projection of this V and I along y-axis at any instant is Vm sin omega t1, and that of current is Im sin omega t1 minus pi by 2. Okay, these projection give the instantaneous value of voltage and current at time t1. So these projection are representing instantaneous value at time t1. Inductor has reactance omega L that limits the current similar to the resistance in DC circuit. Okay, inductor has reactance omega L that we have discussed already. That is inductive reactance that limits the current similar to resistance in the DC circuit. Let's try to find out, does this inductor consume power or not in the next section. To calculate the average power, we need to find the instantaneous power first. So let's see the power expression. It is similar to that we have derived for the purely resistive circuit. Only we have to put the value of V and I according to the inductive circuit. So instantaneous power supplied to the inductor is PL equal to IV, which is equal to Im sin omega t minus pi by 2. This is the value of instantaneous current for purely inductive circuit, and for voltage it is Vm sin omega t. Okay, so this PL, this is instantaneous power supplied, which is equal to minus Im cos omega t. So again I am using the identity sin omega t minus pi by 2, taking negative sign out of this sign, then this will become sin pi by 2 minus omega t. So sin pi by 2 minus omega t will become cos omega t. So this will become minus m cos omega t, Vm sin omega t. Okay, so PL is equal to Im Vm cos omega t sin omega t. Now we will use another trigonometry identity, that is sin 2x double angle property. Sin 2x is equal to 2 sin x cos x. So we will multiply this expression with 2 and divide with 2. So it will become 2 sin omega t cos omega t, which will become sin 2 omega t, and divide by 2. So here is the final expression for instantaneous power, that is PL equal to minus Im Vm upon 2 sin 2 omega t. Now we'll take the average of this instantaneous power. So this is the instantaneous power. Now average power. So average power over a complete cycle will be PL average, which is average of this minus Im Vm upon 2. So this Im is peak value, Vm is also peak value 2. These are constant, so they will come out of the average. Okay, so average of this instantaneous PL will be equal to minus Im Vm by 2, and average of this sin 2 omega t function. We know that average of sin theta is 0. So average of function sin omega t, we will find it now. Average of sin 2 omega t will be, which is equal to, how we will find the average if we are not using standardized formula. So we will find by this integration from 0 to t interval sin 2 omega t dt upon dt 0 to 2t interval. So this is the average of this sin omega t. This is the way how we find the average value. Okay, so sin 2 omega t, average of this sin 2 omega t will be, so integration of this sin 2 omega t will be minus 2 omega t upon 2 omega. Limits from 0 to t. So this, in the denominator there was 0 to capital T dt. So this integration will become small t from 0 to capital T. So after putting limits, it will become t minus 0, which is t. Okay, so how this step came, I have explained. So after putting limits, so cos 2 omega capital T minus, after putting 0, it is cos 0. So after putting this t, this capital T is equal to 2 pi by omega. So put here 2 pi by omega. Omega and omega will cancel out. It will become cos 2 into 2 pi, which is 4 pi. What is cos 4 pi? Cos 0 is 1. Cos pi is minus 1. Cos 2 pi is 1. Cos 3 pi is minus 1 again. And cos 4 pi is 1 again. So it will become 1, and cos 0 is also 1. 1 minus 1, 0. So sin omega, average of the sin 2 omega t will become 0. So average of sin 2 omega t over a cycle T equal to 2 pi by omega is 0. That means average power, which is equal to minus Im Vm upon 2 average of sine 2 omega t, will be equal to 0, and it is represented as capital PL. Okay, so average power dissipated across the inductor is 0. So average power supplied to an inductor over one complete cycle is 0 in case of purely inductive circuit. What is the reason? So this is because inductor absorbs energy due to the half cycle, okay, of the current growth. When current will grow in the circuit, it will absorb energy, okay, and returns the same amount of energy during the other half cycle. When current is increasing through the inductor, the magnetic field produced by this inductor will increase. So magnetic energy stored in the inductor will increase. So during the other half cycle of current decline, when current is decreasing, magnetic field will decrease. So it will return the same amount of this magnetic energy in the circuit. Okay, so this is because inductor absorbs the energy during one half cycle of current growth and returns the same amount of energy during the other half of the cycle. So let's see the example 7.2. A pure inductor of 25 millihenry is connected to a source of 220 volt. Find the inductive reactance and the RMS current in the circuit if frequency of source is 50 Hz. So let's see the solution. So what is given? Self-inductance is given 25 × 10 to the minus 3 Henry and frequency nu is given 50 Hz. To calculate the inductive reactance XL, what is XL? Which is equal to omega L. So we have to find the omega first. So we need angular frequency first. So angular frequency omega is equal to 2 pi nu. So nu is given in the question. So omega is equal to 2 pi into 50. So omega is equal to 100 pi radian per second. Okay, now we'll find the inductive reactance. Inductive reactance XL equal to omega L. So which is equal to 100 pi into 25 into 10 to the power minus 3. XL equal to 2.5 pi ohm, which is equal to 7.85 ohm. Okay, now what we have to find? RMS current. So to calculate the RMS current, IRMS, what is the formula? As already said, voltage given in the question. So if voltage is given in the question without saying anything, so it will be assumed RMS value only. Okay, so as already said, voltage given in the question will be taken as RMS unless specified. So given RMS voltage, VRMS is 220 volt. Okay, and now from the relation IRMS equal to VRMS upon XL, this expression we have seen in the NCERT question 7.9. Okay, VRMS is given, XL we have calculated. Can we find IRMS, which is equal to 220 upon 7.85. So IRMS will be equal to 28 ampere. Got it? So let's have a quick recap. So we studied purely inductive circuit and AC voltage supplied to it. By using voltage source V equal to Vm sin omega t, we arrived at expression for current in this case. I equal to Vm upon XL, that was omega L, sin omega t minus pi by 2. Inductive reactance XL is the opposition offered by the inductor to current and is given by XL equal to omega L. For DC current, opposition offered is 0, as omega is 0 for the DC current. No frequency of DC current. Average power P dash consumed by pure inductive circuit in one full cycle is 0. Only stored during half cycle and returned during the remaining half cycle. Relation between RMS value and current and voltage for pure inductive circuit is IRMS equal to VRMS upon XL. This expression we have also used in the example also. So phasor diagram for pure inductive reactance is given in the figure 7.6a. Okay, and phase difference between voltage and current is pi by 2. For pure inductive circuit, current and voltage are out of phase. They are not in phase. They are out of phase by pi by 2 and current lags the voltage. You have to remember this thing. This is very important thing. That current lags the voltage by how much phase? Pi by 2. So there are some practice questions you have to do yourself. So calculate the opposition offered by inductor of inductance 10 millihenry for pure inductive circuit when frequency of source is 50 Hz. Next question, the average power consumed by pure inductor in an AC circuit over one complete cycle is. Options are maximum, minimum, zero, depends on inductance value. In pure inductive circuit, what lags behind, current or voltage? If phase of current is 30 degree, if the current phase of means the at any instant current phase of current is 30 degree, what is the phase of voltage? So we know that phase difference between voltage and current is always pi by 2, which is 90 degree. So if phase of the current is 30 degree, what is the phase of voltage? Okay, so this is all about today's lecture, but don't go anywhere, we have to do the DPP. Okay, let's do the DPP. In a purely inductive AC circuit, the phase difference between the voltage and current is. You can write your answer in the comment section. So what is the phase difference between voltage and current in the purely inductive circuit? Yes. The inductive reactance XL of an inductor depends on peak value, peak voltage and frequency, inductance and frequency, inductance and peak current, or resistance and frequency. Which option is correct? So XL is equal to omega L. So this inductive reactance depends on, yes, inductance and frequency. If the frequency of the AC source connected to a purely inductive circuit is doubled, the inductive reactance becomes. It depends on frequency. It is directly proportional to frequency. If frequency is doubled, what is the effect on inductive reactance? It will become half, double, 4 times, or unchanged. Yes, double. The average power consumed in a purely inductive circuit over a complete cycle. We have calculated what is the average power consumed in the purely inductive circuit. Maximum, half of the peak power, 0 or equal to instantaneous power. Yes, 0. Last question, an inductor of 25 millihenry is connected to 220 volt 50 hertz AC source. What is the RMS current in the circuit? So this is the same question as example. So what was the RMS current in the circuit? We calculated. You can calculate. I guess we have calculated 28 ampere. Yes. Okay. Well done. All the questions are correct. Okay, so this is all about today's lecture. I hope you enjoyed the session. Thank you.